with a Bachelor's of Science in Business Analytics and in 2020 with a Master of Finance. So today I'm going to be talking about Monte Carlo simulations of probability problems. So for today's agenda, we're going to start off just by talking about why Python is a good tool for computations. And then we'll move on to the famous birthday problem and the equally tricky Monty Hall problem. And then kind of as an added bonus, I'll go behind the scenes at the MathPrize for Girls competition. So first, I'd like to talk about Python as a computational tool. So first off, I'd like to talk about what Monte Carlo sampling is to give some insight as to why we would use it for Python. So Monte Carlo sampling is a process of repeated sampling over a defined probability distribution. So it's used to approximate values that are really hard to calculate numerically. So part of the reason Python is useful here is because Python, along with most other coding languages, utilize a tool called for loops to execute the same process many times. So this is very useful because we don't have to do manual repetition for this, but among all of the programming languages that use for loops, Python is known for being especially efficient and approachable. For folks who have maybe taken AP Computer Science in Java, you know that it can be very challenging to get started. You have to type all these other words just to even start doing anything. But with Python, it's pretty easy to just dive in. So today we'll be using a Python feature called packages, where these packages are not inherently available in a regular Python shell. So we need to bring them in using certain commands in order to help us execute higher level calculations. So the first thing we have is called matplotlib.pyplot. The .pyplot indicates that the pyplot function is coming from a bigger library called matplotlib. So this will help us to make graphs. Second is NumPy, which is a very handy computing package. And the third package is called random, which utilizes randomness to help with our distributions. Now, a lot of the time, there's a little controversy as to if the random package is actually random, but most random packages, they'll give you something like the last digit of the number of milliseconds since Y2K or since 2000. And basically, this isn't technically random per se. It's not like the computer's actually rolling a dice and giving you a result, but it is close enough. So also you'll see down below where it says import matplotlib.pyplot as PLT. What that means is we're importing the matplotlib pyplot function, but we don't want to have to type it out every single time we use it because it's just a lot of words. So by adding the as PLT, that means we can use PLT as a simpler way of calling back the larger named function. So let's start off by talking about the birthday problem. So the birthday problem examines the probability that in a group of a certain number of people, at least two of them will share a birthday. So for purposes of the simulation, we assume a 365-day year where all birthdays are equally likely. So the probability that in a group of a certain number of people, none of them will share a birthday is as follows. So when we start with just one person, we know that there's no way there will be overlap in the group because there's not even two people in the group. When we expand the group to two people, the probability becomes 1 times the 364 over 365 fraction because there are 364 birthdays that the other person could have to not overlap with the first member. Expanding on this to go to 3 birthdays, we have the quantity for 2 birthdays multiplied by 363 over 365, because assuming the first 2 people have different birthdays, the third person has 363 birthdays that they could hypothetically choose from and not create overlap. So this kind of expands as we get into bigger and bigger group sizes. We would multiply by 362 over 365, 361 over 365, and all that from there. So then to find the probability that there is overlap among this group, we could take the complement of all the calculated quantities. So take 1 minus whatever we just found out. So let's see what this looks like when we translate it into some Python. So the first line, no repeats, what this does is it basically makes a list of 366 zeros. So the reason I wanted it to go up to 366 is because I wanted it to show that when we get to 366 people, we know that there does have to be an overlap because there's only 365 birthdays to choose from. So then what line 4 does is it makes it so that the probability of no repeats when there is only one person in the group is just 1. Now the reason this looks to me like it should say that the probability of no repeats in a group of 0 people is 1. However, Python is a programming language that utilizes something called zero indexing. So the first position in a list, instead of being called the first position, is actually called the 0th position. So the 366th position in the list that we created is actually referred to as place number 365. So we have to be kind of careful with that, with how we kind of do housekeeping with indices. So the 0th term, the way I set up the list, responds to there being one member in the group. So now for line 7, for I in range 1 through 365. So basically what this means is that we're going up for all the, we're calculating all the values for all the other list items. So basically what we do is for list position 1, which because of the 0 indexing being weird corresponds to 2 people, we're taking the probability item that corresponds to there being 2 people in the group by taking the probability of what there being no overlap in the 1 minus or the one smaller group and multiplying it by the corresponding fraction. So like the 364 over 365 for 2 people, or the 363 over 365 for 3 people. Yeah. So again, it's a little funky with the housekeeping because it's 365 minus I instead of minus I plus 1 or anything like that, just because of the consistency with the 0 indexing. So now, because of the complement that we talked about, I wanted to also make a list of the probability that there is a repeat within a group of a certain size. So what I did for that was I took a list of 366 ones and then just subtracted the probability of repeats, because that's an easier way to find the complement than doing a big mathematical function. So here on the right, this is what it looks like when we successfully plot the probability of repeats for between 0 and the 366 people. We can see that it gets fast, or it gets high pretty quickly. So for our simulations, I decided to cut off the group size at 75 people right at the beginning of the plateau. So in order to do Monte Carlo simulation for the birthday problem, I've decided to make a bunch of simulated groups, and we're going to look at if there is any overlap within the groups and then go from there. So what this birthdays range does is I wanted to have birthdays represented by the numbers 1 through 365. So what this range function does, so it looks like it should go from 1 to 366, but the funky thing about Python ranges is they always cut off right below the higher number. So what this range does is it will go from 1 to 366 with a step size of 1, so meaning it goes 1, 2, 3, kind of just on the whole numbers. However, it won't actually make it to 366. It will just cut off at 365. So this is kind of another housekeeping thing. So then I made 2 of what's called helper functions, which are little shorter functions that get called when you tend to do something bigger. So these kind of do like some smaller level housekeeping for the kind of bigger functions. So the first function I made creates a group of birthdays for a given size. So what it does is it takes the size of the group in as an input, creates an empty list, and then for every person in the group, so this means for the number of times as there are people in the group, we're going to add a random choice of birthdays. So this random dot choice shows that the choice function comes from the random package that we brought in the beginning. And then when it says to return the group, that just means to show me the group that you came up with. So then in order to see if there are repeats within the group, the function on line 9 kind of is a helper function to tell us that. So what the set function does is it basically creates a condensed list of every unique term in the larger list. So if the group has all different birthdays, the length of the set of the group will equal the length of the overall group. However, if the length is different, the length of the set would be shorter because there were overlapping birthdays at hand. So basically what I had to do is that if there are no overlaps, I wanted it to return a 0, and otherwise I wanted it to return a 1. The reason I did 0s and 1s instead of a true and false is because this will actually be a really handy tool for us in calculating probabilities later on. Does anyone have any big questions so far? If you do, you can feel free to put it in the chat or unmute yourself if you need to. I'll check back on it in a few minutes anyway. So basically, now what I did was I used the helper functions that I made earlier to do 3 sets of calculations. So the upper left set is we're only doing 100 simulations for each of the group sizes from 1 to 75 members. Upper right, sums 1,000 and everything, we're doing 1,000 simulations for each size of group. And then on the bottom, this corresponds to doing 10,000 simulations for each size of group. So let me walk through the example on the upper left with just 100 sums so that we can all go through the process. The first step is for me to make a list of 75 zeros. So that corresponds to the group sizes of 1 through 75 people. Next, I do what's called a for loop to do the iterations without doing them manually. So for I in range 1 through 76, also, just as a heads up, if you don't put the third value in the range function, it just automatically assumes a step size of 1, so that's okay. So for I from 1 to 75, because the range cuts off at n-1, I have this sum 100, which starts off as a 0, and we'll see why I have a sum variable in just a minute. So for j in range 1 to 100, so basically we're just doing this 100 times, the new group, we add the result. So we make a group for each people's birthday. So it's a certain number of people and their birthdays. And then to the sum, we add to see how many repeats there are. How many of these 100 groups have repeats? So then we divide by 100 to figure out the actual probability expressed as a decimal. So this is the same what we do for all the other two, just with more simulations to understand it. So as I plot the 3 values for 100 iterations, 1,000 and 10,000, we can see really big differences in smoothness, particularly as we go from 100 to 1,000. A lot of times with Monte Carlo simulations, it's best to do as many as you can. However, for some people, the strength of your computer is a limiting factor, or things like memory and processing power. So you also want to, approach it safely, kind of start at a lower number and then go up doing more simulations to see if that's how you like it. So now let's see how the 100 trials gets pretty close to the graph of actual probabilities. However, as we go to the 1,000 and then the 10,000, we see that it really does a much better job of mirroring what is originally happening. So since I don't see any questions in the chat box, I'm going to just move on to the Monty Hall problem. So the Monty Hall problem is named after the original host of a game show called Let's Make a Deal. So Let's Make a Deal involves there being a contestant who has to pick between 3 doors with the hope of winning a prize. So the way the show is structured is that the contestant chooses a door, and then the host opens a door that has no prize behind it, and then the contestant is asked if they would like to switch their choice of door or if they would like to stick with their original door. Now, on today's version of Let's Make a Deal, the fake prizes are called zonks, which, as we can see in the monster on the right of the screen, they're getting a little more aggressive in their nature and more just disappointing in general. So the way that it's originally structured is by people to talk about there being goats and cars. So you assume that the person wants a car and that behind every other door is just a goat. So the box on the left of the screen is saying that if we assume the person picks door number 1, we're assuming that the car has a 2/3 probability of being behind one of the 2 other doors and a 1/3 probability that the car is behind the door you originally picked. So then on the right, what they're saying, which is kind of the biggest confusion point in the Monty Hall problem for people, is that we're assuming that there's still a 2/3 probability that the car is behind one of the doors in the box. However, since we know that door number 3 just has a goat, we're now phrasing the probability that the car is behind door number 2 as 2/3 because it's still the probability that it's behind one of the doors in the box. So now if I expand this to be with 4 doors, let's just bring it up one at a time. So same logic on the left, I have a 1/4 chance of just picking the correct door originally. Now let's say the host opens door number 5 to show me that there isn't the prize behind it. Sorry, door number 4, not 5. So in the situation on the right, I have a 1/4 chance of winning the prize if I just stay in door number 1. However, looking into the box, we notice that there's a 3/4 chance the correct door is somewhere in this box. And also, now that there's only doors 2 and 3 in the box, I have a 1/2 chance of picking the correct door within the box. So with those conditional probabilities, if I switch, I actually have a 3/8 chance of success, when I only have a 1/4 chance of success if I stay in door number 1. So now let's expand this to a bigger number of doors. So there's a 1/n chance that I win the prize by just picking the original door and going with it. So then there is an n-1/n chance that the correct door is somewhere in this box. So if I choose to stay with door number 1 instead of switching to one of the others, I have a 1/n chance of winning the prize. Now if I switch doors, there's an n-1/n chance that the correct door is somewhere in the box. And then there's a 1/n-2 because I wouldn't pick 1 or n, that the correct door is chosen after the door is opened. So this gives us a total of n-1 over n times n-2 chance that you win after switching. So this is a little bit of a doozy, but we can make it through it. This is a function to simulate a Monty Hall problem. So basically what this starts off as, we have the number of doors and then switch. So switch will be entered when you run the function either as true or false. So this is called a Boolean variable. So within the function, the first thing that I do is make a list of the doors. So the range 1 through number of doors plus 1 means that we get doors 1 through n. So door names and regular doors are the same thing because I wanted to operate under the assumption that, all doors start off as regular doors and then the prize is put behind one of them. So prize door is supposed to be a random choice. So again, using the random package of the door names. So basically what that means is we pick randomly from the list of all doors to find the one that we put the prize behind. And then we remove that list, that name, from the list of regular doors. So now regular doors just has all the zonks in them and not the prize door. So the person can choose the door that has the prize or one that does not have the prize. So on line 9, we have that the person's choice is just a random choice of all the door names because they're allowed to pick anything. So now the first door that the host always shows is a door that does not have a prize. So the list of doors that the person can pick from is just going to be the same as the regular doors, which is indicated on line 11. So moving down to line 13, if the person has chosen a regular door, we do not want to show them that regular door. We want to show them a different one. So if the person chose a regular door, we're going to remove that door from the list of ones that can be shown. So then on line 15, the first door shown will be a random choice of whatever is left. So once again, kind of tying in that random function all together. So this is where the switch comes into play. So if the person decides to switch doors, we need to make a list of all the doors that they can switch to, which we know that if there's n doors, then there's n minus 2 that they can switch to. So line 18 makes a list of all doors. Line 19 removes the one that a person chose. Line 20 removes the one that was the first door shown. And then the person's choice picks randomly from what's left. So then if the person's choice is equal to the prize door, then we return a 1 and it worked. And otherwise, it's just we return a 0 because it didn't work. So now for the Monte Carlo problem, I decided to set up 2 vectors that talk about the probabilities in each situation so that we can compare the simulations to the actual values. So for actual switch probabilities, this is the probability, the actual mathematical probability of winning if you switch. So I just made it as a list of 100 zeros, and then I populated the first 2 elements with just 1 because if there's only 1 door, you have to win, and if there's only 2 doors, then you would also just win. So for actual stay probabilities, these are all correspond to just 1 over n because you pick your door and you stick with it. So what I did for the stay probabilities is I made a range from 2 to 100. So what this does is it goes from I values of 2 to 99, which corresponds, because of the 0 indexing in Python, to there being 3 doors all the way up to 100 doors. So the actual stay probabilities for each index is going to be 1 over I plus 1. And again, because of the 0 indexing, we need to use I plus 1. So that for position 2, which represents 3 doors, we get 1/3 instead of 1/2. So now on line 12, we discuss what to do in the actual situation. So for the switching probabilities, the range is adjusted a little bit differently because we have an n minus 2 on the bottom. So if I started with I in range of 2 and tried to do that, Python would be extremely upset with me. So now what we do is we start with 3 to 101. So this will give us I values between 3 and 100. So then what we do is we do probability of the actual switch probability for index I minus 1. So starting with index 0.2, which corresponds to 3 doors, equals this formula that we had come up with from before. So now for the actual simulations. We have door numbers. This range shows the number of doors from 3 to 100. And this is all we care about because with 1 and 2 doors, this is really not very interesting. So the Monte Carlo switch probabilities and stay probabilities, it's a list of 98 zeros to correspond between 3 and 100 doors. So now what I did is the sum for switch and the sum for stay start off as 0. So, sorry, to start at the top of the function, we go for every possible number of doors we have. We have the sum switch and the sum stay. So then, because we're doing 100 simulations, we do this. And then the sum switch and the sum stay, we add the 0 or 1 value to the two sums. And then we do division here to calculate them as decimals. And the I-3 kind of moves them to the proper indexing to correspond with the graphs. So as we can see, the switch and stay probabilities are both mirrored even pretty well by the 100. However, with the 100 probability simulations, there's still enough variance within them that it's not a strictly decreasing function all the time, which kind of indicates that we need to have more trials since we know that that's how it should be. So now when we move it up to 1,000 trials, we can see that it's a lot smoother. Things are also smoother with the switch probabilities than the stay probabilities because in some cases it's easier to estimate a more extreme probability. So now when we move up to 10,000, both of them are extremely smooth and they do a very good job of mimicking the actual probability values. So as you can assume, if we kept going with this, it would keep getting better and better the more trials we ran. So I was also asked to go a little bit about behind the scenes at the MathPrize for Girls competition, which I have volunteered at and worked at over the past 7 years. So MathPrize for Girls is put on by an organization called the Advantage Testing Foundation. So this is the largest math prize for girls in the world. So each fall at MIT, about 300 people come together to take the test that is created for the competition. So the ultimate goal of the competition is to promote gender equity in STEM professions and to encourage young women to become mathematical and scientific leaders by sticking with a hobby that they already like to do. So the testing criteria to get into MathPrize, you have to submit an application with registered test scores on the AMC. And the cutoff tends to be sort of around the cutoff for the Amy Invitational exam. So the point of MathPrize for Girls is to encourage more women to join and retain in STEM professions, because currently as it is, participation is much lower among women than men. And STEM careers are also very prosperous and generally very stable, so they're a good choice for everyone to participate in if it aligns with what you like to do. So in figure 1 on the left, you'll see the percentage of female graduates from tertiary degrees, which means colleges, in selected subjects in 6 different countries around the world. So the yellow represents science and technology, so the STEM kind of things, and gray also represents certain engineering in the more manufacturing types. So you'll see that only 30 or so % of STEM grads in the USA are female, which is actually in some cases lower than our counterparts in South Africa and India, as well as Turkey and Indonesia. Additionally, in terms of the number of STEM degrees by gender in the US, we can see on the right that the disparity exists at all 3 levels of degree: bachelor's, master's, and doctorates. The proportions are pretty much the same throughout, where it looks to be roughly twice as many male participants in each sort of degree program. So why do I like MathPrize for Girls? So what I like about it is that it has an extremely positive and respectable tone in all of its conduct and sort of general vibe. So MathPrize for Girls, it's a very strict cutoff and a very difficult competition. One thing I learned from helping at the award ceremony is that the top scores tend to be, out of the 20 questions, roughly around 14 or 15 questions. This is not an artificially easy competition, nor is it meant to be something that everyone is ragingly successful at. The event is focused on showcasing what girls can do while understanding their role in a diverse world. So it's focused on preparing girls to compete at the highest levels of math instead of kind of lowering the bar or any sort of thing like that that's artificial. Additionally, what I like about this competition in particular is there is a big emphasis on socialization with other contestants, and people can also reconnect with old friends and make new ones at the games night as well as the contestant lunch. So it's a very holistic experience that's focused on mutual support. And the last thing that I really like about it is that it's a weekend long competition that never uses the word boys, because we don't need to talk about people that aren't in our group in a negative way in order to understand what girls can do. We don't need to put others down in order to build ourselves up. This is just a celebration, and it's supposed to be very positive. So the biggest part of MathPrize for Girls is volunteers. So if you're in college, there might be other math competitions that you could volunteer for as well. But I know a lot of MathPrize volunteers come from MIT and Harvard, as well as other colleges in the Boston area. So volunteers work throughout all parts of the competition. There's the checking people in and making sure everyone's registered and has the appropriate ID. There's also a games night, back to the socialization point, and the biggest thesis of game night is that there's no parents allowed. Some people will try really hard to violate that, but you have to stop them at all costs. There's also dorm buddies, which is older current college students that will volunteer to host a participant in their dorm for the night, so kind of offsetting some of the financial cost of the competition, which is always great. And then proctoring the actual exam, this is kind of just to be in the testing room to make sure that, everything's going okay, if anyone has a question or concern. And then there's also grading the exam, which is mostly done by professionals. And then there's also just ushering and helping people at the award ceremony first to, get into the right space, and then also for things like airport vans, other just kind of helping people even maybe find the restroom or figure out where to get a t-shirt, just kind of generally being aware. So even if it's not MathPrize for Girls, there will probably be some opportunities at your colleges to pay it forward in these kind of scenarios. So it's about kind of finding, which sort of volunteer position works for you. For me, since I'm very social, I prefer to do the games night and the ushering as opposed to things like the proctoring and grading, which are more quiet, but some people find that those other things work better for them.
We have a question in the chat.
Yeah.
That's how old do volunteers have to be?
So they have volunteers that are starting as freshmen in college. I think that if you're in high school, they'd rather see you try to participate, if that makes sense. But any college student or above could volunteer. So that's actually the last of my slides. So I was thinking that I could just open it to other questions if possible. Oh, so we did have another question. Sorry, I'll turn this on. We did have another question about you have to live in the Boston area to participate. And the answer to that is no. You can apply from anywhere. We have also had people, I think even from Canada, we've had people from Canada. A lot of people come from California as well as even Florida. So there's a ton of also like hotel arrangements and everything that you will have to make on your own, but there's a lot of hotels in the area that are used to the event for sure. Is there anything else that people... Oh, so I don't actually know what they're going to do about it being online. I think, unfortunately, they may not have fully made the call on that yet because it's being hosted at MIT. And I think in a lot of ways with regards to schooling, MIT might not even fully know what they're doing. I keep seeing emails that are appropriately non-committal. So I can also... Preston, if I give you a link, if I send you a link later to MathPrize, could you send it out to your students Would that be okay?
Yeah, of course.
Okay, perfect. So I'll make sure so that everyone can have the chance to learn about it. So moving on to Ezra's question, I feel like a lot of Monte Carlo has been used in finance simulations. A lot of it, this may be a little bit biased because my master's degree was in finance, so I saw it a lot. But I definitely think that there could be applications in a lot of other probability areas. Also, I can imagine certain life sciences would probably use it, especially with a lot of random factors regarding things like health and disease transition. But the biggest thing I know is definitely with finance, and it can be a little more involved when people are doing financial modeling because sometimes it could involve certain more complicated distributions or other events called that they call shocks. So things like building in variables for what happens if the economy crashes again, and then they run your finances 10,000 times to say, okay, like you have enough for retirement. That's definitely the biggest case I've seen it used in. Does anyone else have a question they'd like to ask in the chat? So I think it looks like everyone is all set for now. Um, if I was not correct in that, you can definitely reach out. Oh, yeah. Yeah, the codes can definitely be made in other languages. The ones that I have used the most are Python and R. People, programming languages, it's one of those things that the more you know about them, people tend to have like very strong opinions on one. So most people just kind of tend to take what their favorite is and stick with it. But what I like about R is that it's also pretty approachable like Python. The first language that I really got into was Java, which I didn't like because of the very clunky setup. But with R, one thing that's different than what I showed today is that R is actually one indexed. So you'd have to be kind of careful about how you do the ranges and everything to make sure that it's in line with that. Yeah. Oh, so this is a good question. For a very rare event, like one in a million, honestly, the best way to properly simulate Monte Carlo is unfortunately you just have to do it like a lot more. So this kind of goes back to things like processing and also using like helper functions. There are other things you can do as you get more complicated to make the code run more efficiently so that if you do have to run it millions of times, it only really takes a few minutes. But unfortunately, for these very rare events, you do have to do just more iterations over and over again. But that's why I do suggest that people start with fewer just to make sure that your computer is running at an appropriate speed. And also, if you are doing something like this and you want to make sure your computer's doing okay with it, for in the for loop where it's like for I in range, like 1 to 10 million, you could have it print out an update like every million or so iterations just so you can make sure it's running kind of how you'd like it and it's making appropriate progress. But thank you for that. That's a very good question. Oh, I think Monte Carlo actually refers to, let me just double check. I think Monte Carlo refers to a casino. Yeah, it's a casino over in Monaco. So I think it was kind of based on probability of gambling. Yeah, exactly. But Monty Hall was a person. I think now Let's Make a Deal is hosted by Wayne Brady. So it looks like we seem like we're all set for questions, but just know that if there's anything that I didn't cover or that you'd like to know more about. Oh, sometimes mathematicians work at casinos, but if you're winning a little too much, they don't take very kindly to that. So if you do come up with something interesting, you have to be, a little careful about how you execute it. But yeah, if anyone has any further questions about MathPrize or anything like that, Preston and Jed and everyone, they have my contact information, so they can definitely help put us in touch. Yeah.
All right, yeah. Thank you for coming here and presenting today. We really appreciate it.
Yeah, anytime. Thank you all for, showing up in all your different time zones and everything.